Let's look at lactaldehyde. So this molecule has three carbons, 1, 2, 3. So it has a propyl group. In the first carbon has a carbonyl. This is a double bond, oxygen with two lone pairs, and there is a pi bond here. So this cannot rotate. So this is a carbonyl with one of the substituents being hydrogen and one being carbon. So this is an aldehyde functional group. So this carbon is connected to an aldehyde functional group. That is the second carbon. The second carbon is also connected to an alcohol here. These are the two lone pairs of the alcohol. Here is the hydrogen atom on the alcohol, OH group. And this carbon is also connected to a third carbon. This is a methyl group, a CH3 group here. This carbon is also connected to a hydrogen atom. So as you can see, in this lactaldehyde, you have three carbons, and the central carbon, C2 carbon, is connected to four different functional groups: an aldehyde, an alcohol, and a methyl group, and a hydrogen. So as you know, a carbon which is connected to four different functional groups is a chiral carbon. So when it's a chiral carbon, you can use the Kahn-Ingold Prolog rules to assign preferences for these substituents on this carbon, chiral carbon. So how do you do that? First you give the preferences according to the atomic number. So the highest atomic number gets the first preference, and the lowest preference. So oxygen here has the highest atomic number, so that gets preference 1. And the next you have two carbons, out of which this carbon is substituted to an oxygen, whereas this carbon is substituted to only hydrogens. So this gets the second preference, and this gets the third preference, and this gets the fourth preference. So the fourth preference one goes behind you in the plane facing the paper here, and the rest of the groups face towards you. Now, as we saw, the preferences 1, 2, 3. So this is in the anti-clockwise direction. So it is S configuration. So this is lactaldehyde with S configuration. The IUPAC nomenclature for this is 2-hydroxy-propanal or propanaldehyde. Okay. Now, this is a chiral molecule. Now, interesting property of chiral molecules is that they can have configurational isomers. Now, let's look at the structure of its configurational isomer. This is lactaldehyde, which is with a D or R configuration. Now, let's look at how this is R configuration. Okay, you can see that it looks very identical to this. This molecule is also lactaldehyde, and it looks very identical to this molecule. But you can see that they are mirror images of each other. First, let's understand the configuration of this molecule. If you see, the preferences remain the same. Oxygen gets the first preference. This carbon is connected to an oxygen, that is alcohol, an aldehyde, and a CH3 methyl group and a hydrogen group. So when you take the hydrogen as the behind you towards the paper, the groups that project in front of you, you assign the priorities 1, 2, and 3, and you can see that this is in the clockwise direction. So this is R configuration. So this is R lactaldehyde, and this is S lactaldehyde. Now you can see that these are mirror images of each other. Let me rotate it in different. I'll do C3 rotational operations. You can see that this is also rotational mirror images of each other. If I rotate it by another 120 degrees, these are also mirror images of each other. And I again rotate it by another 120 degrees. I come back to the same two molecules, same two orientations, with both of them being mirror images of each other. The speciality of this is that These are mirror images, all right, but these are non-superimposable mirror images. When you look at these two structures, if I try to superimpose one upon the other, you can see that this CH can sit upon this CH and this CH3 will sit upon this CH3. However, this alcohol is sitting upon this aldehyde, whereas this aldehyde is sitting upon this alcohol. There is no way by which I can perform any operation, any rotational operation or any operation by which these two can be superimposed upon each other. So they are not identical to each other in that sense. The only way that they can be made identical is that you remove this bond and exchange them between each other, then you get to identical molecules. So these are called configurational. They are isomers, but they are configurational isomers, where you have to break a bond in order to and exchange two of the groups in order to get to the other molecules. So these are R and S configurations of lactaldehyde or 2-hydroxypropanol, both of which are chiral molecules having one chiral carbon each, and they are enantiomers, non-superimposable mirror image structures.